introduction to his background. So Tobias Kippenberg is a full professor at EPFL in Lausanne in Switzerland. And he is a full professor since 2013, and he joined EPFL initially as an assistant professor in 2008. Before joining EPFL, he was actually in Munich, or let's say in Garching near Munich, in the Max Planck Institute there for quantum optics. And during his time in Munich, he discovered a few new processes like the radiation pressure cooling of optical microresonators, and also the optical frequency comps in very high quality microresonators using the Kerr effect. So these two discoveries at that time also made him very famous in the community with a lot of publications. In fact, he was the most cited physicist from 2014 to 2019. And of course, he has received many awards for his discoveries, including the EFTF Award, the Helmholtz Prize, and so on. Actually, your list, Tobias, is too long. I cannot really read all of them, okay? But we have that in the proceedings for those who want to check it in detail. I should say that Tobias also has a good sense for business, I think, and he is a founder of a company, Legentech, in Switzerland, also in Lausanne. Legentech makes integrated solutions for photonic integrated circuits like silicon nitride waveguide kind of technology, and you're involved in many other things. So Tobias, we are very happy that you are here now. Of course, we wish you could have joined us in person as originally planned, but we are happy, very happy that you can join us online now, and we look forward very much to your presentation.
Yeah.
Please welcome Tobias.
Yeah. So yeah, thank you very much. That was a very, very kind introduction, and I regret that I cannot be in Basel, but I hope that I'm available after the session, and I hope we can at least via Zoom take contact for any questions. And so, even though I regret that I cannot be there in person, I do enjoy that I can give this presentation today to you. And for the talk, what I'd like to talk about is our work on what I like to call hybrid non-integrated photonics. I'd like to tell you about the advances that we made that now allow to create devices ranging from chip-scale frequency combs to novel devices that we have been more recently investigating, in particular frequency-agile lasers that can be used, for instance, for LiDAR, and also erbium doped waveguide amplifiers. And this is recent work that was just published I'd like to highlight in particular in this talk. As already mentioned by session chair, I do have we have transitioned our technology also to companies. I'd like to mention that a lot of the work I'll be describing is about silicon nitride. We started Legentech with two co-workers about 6 years ago. It's a foundry that's operational from Switzerland, but also fabricates in the X-Fab in Paris, and is commercializing the low-loss nitride we've developed. I'd also like to tell you and introduce to you some of the technology that we're right now working on, in particular with deep light on FMCW lasers and related technology that is just about to spin off from the lab. Okay, so what I'd like to first jump into is to tell you about one of the core photonic integrated platforms we're working on, which is silicon nitride. And even though silicon photonics right now is pervasive, it's being used in data centers, silicon itself is not an ideal material for photonics because it has a band gap that limits light propagation in the visible, and moreover, the band gap also makes it susceptible to true photon absorption. So despite the remarkable success of silicon photonics, it's not inherently a very good material to make very low loss integrated photonics that also can operate in the nonlinear regime. Now, one material that is distinct in this regard is silicon nitride. And silicon nitride is a well-known material in the semiconductor industry. It's used as a stressor layer in silicon transistors. It used to be used as a stressor layer. It's also used as a protection layer, so end cap protection for transistors or edge stop. But typically, in its use in semiconductor industry, it was limited to very thin kind of thicknesses of typically tens or hundreds of nanometer. For integrated photonics, it has a number of distinct advantages, including a band gap of 5 eV, a refractive index of 2.0. It's a CMOS certified material. It has transparency window that extends all the way down to the blue and the long wavelength range to the mid-IR. And it has a high effective nonlinearity, about 100 times higher than optical fiber, and no two-photon absorption in telecom window. And it's also space-compatible material. Now, it's only fairly recently, over the last 10 years, that fabrication advances, some of which I'll outline, have allowed to create thick silicon nitride waveguides that allow tightly confining integrated photonic circuits with very compact footprints that benefit from this higher effective nonlinearity and also low propagation losses. And so today, silicon nitride is emerging as a new platform, or a platform in itself, next to silicon photonics that's very well established. And this is really the story I want to tell you today, the journey that we've gone through over the last decade, starting out with our original motivation to make chip-scale optical frequency combs, which we demonstrated for the first time to operate in a solitary regime in about 7-8 years ago in silicon nitride. It's now, silicon nitride has become a material that is the basis for frequency agile low-loss lasers, also parametric amplifiers, erbium amplifiers. It can be heterogeneously integrated, and as mentioned, it's very commercialized now through Ligentech and probably other foundries in the world that are following suit. And so it's becoming clear that silicon nitride is a very interesting platform to realize a range of novel devices. I'd like to highlight in this presentation, 3 of these devices. One is solitary microcombs, so chip-scale optical frequency combs. And building on this work, we realized that by adding another more materials, such as aluminum nitride for actuation, we can create hybrid integrated photonics that now operates with very narrow line width and very high frequency agility. And what I'd like to mention early in my talk is that presently integrated photonics is undergoing, based on silicon nitride, a very interesting transition, because we can make lasers that are not only more compact and are scalably manufactured, but also in the performance metrics can in fact either achieve on par or even better performance than traditional bulk lasers. And I'll talk in my second part on the presentations about some of these technologies that we have commercialized with Deep Light. Okay, so this is again a topic I want to focus on: optical combs, frequency agile lasers, and erbium doped fiber amplifiers. And the underlying really advance that allows to harness these devices is really the low loss. And so generally speaking, one of the very important developments in science and also technology has been the work of Kao to understand how to make fibers low loss. And the very reason I can talk to you today right now here from EPFL is because we have optical fibers with 0.2 dB per kilometer. And Kao identified the limiting factors for absorption in the material to make it very transparent. Now, what's still very interesting is that if, until a few years ago, if you were to go to a conference of integrated photonics, the losses that you would typically have in integrated photonics would be dB per centimeter. So even the most advanced chips that you order from global foundries made using very advanced tools, made in silicon, they would typically have 1 dB per centimeter loss. And what we can achieve today in tightly integrated photonics is losses that are on the level of 1 dB per meter. So these are a factor of 100 improvement over silicon, and we're pushing to close the gap actually even further. There's fundamentally no reason that silicon nitride should not reach a similar transparency window actually than that of optical silica fiber. Now, what is the impact of these very low losses? We can make very power efficient optical comb generators, narrow line with lasers, and as I'll describe today, also a new generation of erbium doped waveguide amplifiers. So how can you achieve and close this gap? And so what we've developed in my lab over the last decade is a novel fabrication method that's called the photonic Damascene process that overcomes a lot of the challenges of traditional manufacturing of integrated photonic circuits based on silicon nitride, which is chief among the crack that forms when depositing thick silicon nitride layers that have a very large innate stress. With this process, what we can achieve is waveguides that have losses now of 1 dB per meter, and the process itself is not a subtractive process, but it's an additive manufacturing process. How does it work? It's called photonic Damascene process for its cousin in the semiconductor industry, the VLSI interconnects, which are made using the copper Damascene process, whereby you deposit successively metals in trenches, or copper in this case, and polish the top surfaces to create these interconnects that exist in typical ICs. So this copper process, again, also used, of course, to make these ornaments, we have adopted for integrated photonics by first etching a silica preform out of glass, depositing LPCVD silicon nitride and afterwards using a CMP process to create integrated photonics. So with this, we can create integrated photonics using a process that does not need the etching of silicon nitride, which is a material that's very challenging to etch. However, this process still does not address the fundamental question of how to achieve very low optical propagation loss. And that problem we solved using a further kind of technique we introduced, and that is to apply, to the preform a slight softening, glass softening process by heating the material up to the softening point of 1250 degrees Celsius. And with this, we can remove, any striation that's left from the oxide etching and create exceptionally smooth sidewalls while retaining actually the lithographic precision that we need, for many of the devices that we're designing. And this process leads to integrated photonics that can have truly exceptionally low loss. And I want to give you one example. So here is a 1-cent coin with a 5x5 millimeter silicon nitride chip. What you see here are two spirals. They can be densely spaced, due to the tight confinement and high refractive index of silicon nitride. And you see here two spirals that have a length of 1 meter. So we're wrapping 1 meter of optical path length, now on a chip basically of 2.5 by 5 millimeters. The losses of these devices here have reached now levels of less than 3 dB per meter. The best we have is about 1.7 dB per meter. And we understand where these losses are coming from and have active programs in my group to actually push this even further. Now, what does this imply? This implies that the devices can act actually as nonlinear generators of light, including optical frequency comb generation, but also make them uniquely suited to replace components that are traditionally fiber optical based. So in this case, such as erbium doped fiber amplifiers, which need long interaction length, and also be miniaturized using this process. So over the last years, my lab has not only looked at nonlinear processes, but also has made advances in endowing the platform with further functionality. We've demonstrated recently that we can add lithium niobate via bonding techniques directly wafer scale to the process, and thereby create devices where you can transition out of silicon nitride into lithium niobate for optical modulation. And this transition can be exceptionally low loss. In our archive paper, we demonstrated 0.1 dB per meter, 0.1 dB interface loss. You can also achieve amplification of 3/5 on chip, which is something we investigated with a group of John Bowers. With Sunil Bava, we demonstrated that we can integrate heterogeneously aluminum nitride and MEMS material for actuation. I'll talk briefly about this as well. And also you can integrate detectors, which is something Ligentech has already demonstrated in several works. So the silicon nitride itself is now not only low loss, but also has additional functionality, be it for modulation or be it for light generation or be it for stress optical actuation. So, it's emerging that this platform really allows a novel of number new devices, and the devices I'd like to talk about today are, on the one hand, erbium doped fiber amplifiers, but also I'll briefly touch upon the topics of frequency agile lasers and ways to also harness the properties of lithium niobate. And as mentioned, as advertised, our chips are used, are commercially available of silicon nitride. They're commercialized by Ligentech and also used actively in R&D. And one paper we're very happy to see is from Xanadu, a Canadian quantum computing company that actually uses our Ligentech chips for photonic quantum computing. So it shows you the range of applications of silicon nitride, from the very fundamental to really technology that is already at the transition phase. So very briefly, what do these low-loss silicon nitride devices allow to harness? The first example is nonlinearity. We can generate optical frequency combs with these devices at exceptionally low power of just a few milliwatts. And so optical frequency combs are equidistant lines of lasers that can be generated typically by femtosecond lasers. And they're a Nobel Prize winning technology that was invented by Ted Henge and my former mentor and Jen Hall. And they are integral part of any optical atomic clock because they provide a link from the RF to the optical, but also can be used to actually synthesize optical frequencies or to generate low noise microwaves. And so these are traditionally also bulk tabletop fiber-based devices, and with optical microresonators, in particular by using the kernel linearity, we can generate solitons and optical microresonators and generate very short optical pulses. And so I will not spend much time on the soliton physics, but I'd like to mention if you scan across resonance, okay, of one of the high Q integrated resonators, what will happen is you will break up the CW light actually into a modulation stability, into a chaotic waveform inside the resonator. That, when you go through the bistability of the cavity, becomes a soliton. And over the last, 10 years, we have really explored many facets of the soliton, both the dynamics, but also different applications of these solitons. They're very fascinating devices, incredibly stable attractors. These dissipative carrier solitons, which are double balance of nonlinearity loss, nonlinearity and dispersion, as well as parametric gain and the loss of the cavity, have a number of unique properties, including being low noise, broadband, and also have a pulse bandwidth that is tunable via detuning and can even reach just a few cycles. So in silicon nitride, we can generate these very efficiently, now in a fully kind of foundry compatible material. And this is an example of one of our devices generated a few years ago in silicon nitride. Whereas in early works in 2016, the pump power to generate the solitons was about 10 watt. We can now achieve this with power levels of tens of milliwatt directly from a DFB laser that is either hybridly integrated or integrated via heterogeneous integration. So it shows you that these low losses are really imperative to also make these silicon nitride microcombs practical for applications where power levels matter. Now, these microcombs can be used for many applications, and I just want to highlight a few that we've been engaged in. There are many more. We've shown with a group of Christian Kuz that they can be used for coherent optical communication. I'll return to this actually in the later part of my talk briefly. You can use them also for fundamental science like spectrograph calibration, where the large mode spacing is imperative to differentiate different pixels. And a new application that we came across that we're very actively pursuing in my group is massively parallel coherent LiDAR. And here, each optical frequency comb line actually is frequency modulated. The soliton actually can sustain external perturbations, and thereby we can chirp very fast the carrier envelope frequency of the comb while keeping the repetition rate constant to first order. And with this, we can achieve a massively parallel array of FMCW laser lines that are could be interesting to achieve video rate LiDAR imaging using FMCW, so frequency modulated continuous wave LiDAR, which is a new sensing modality that gives you in each pixel both velocity and distance. Other applications include neuromorphic computing, and also to give you an example, the most compact device we've made is together with John Bowers' group, where we use both hybrid integration and heterogeneous integration to fully integrate also the 3.5 gain material, both on chip and also off chip using directly butt coupling. So, so this is one facet of the silicon nitride, which is to use the inherent carrier linearity to generate optical frequency combs. And I want to now present to you a very recent application that was published earlier this year by Yang Liu in Science, which is about using low-loss silicon nitride to make erbium doped waveguide amplifiers. And what you see here is one of our EDVAs, which uses 0.5 meter of a spiral waveguide doped with erbium. And so very briefly, erbium doped fiber amplifiers are at least as important as optical fibers. They're the backbone of all of the modern optical telecommunications. One reason right now optical telecommunication occurs at 1550 nanometer is not just the low loss of fibers, it is in fact the presence of erbium, which coincides actually with the low loss absorption. And erbium has a very long tradition. Already in 1965, actually, there's the first papers by Schnitzers that demonstrated erbium-doped gain media and glass rods pumped by flash lamps. The real breakthrough came in 1986 by, in this case, Desouvier, Gilles, and Payne, who demonstrated the first erbium-doped fiber amplifier. And very quickly, this technology has taken off and has become pervasive, and is basically the underlying technology that is used to create the link spans that we need to create a really global communication network, and have allowed in particular to replace electrical repeaters. One question, of course, that comes into mind in this case is, can you also make, so first of all, why is erbium such an interesting gain medium also for integrated photonics? And so first of all, what makes erbium stand out is it's not only that its light emission is 1550, it actually has a very long lifetime. Its lifetime of erbium is about 50 milliseconds in glass. It's a bit shorter in silicon nitride. And this is due to this parity forbidden transition that you have due to the Hund's rule. So transitions are lying very close to the nuclei and you have closed outer shell electrons. And so this rare earth property makes this gain medium very desirable. You have slow gain dynamics, and this in particular for telecommunication leads to very little interchannel crosstalk. And for this reason, evidently, erbium is used for long-haul communications and channel repeaters. There's also very good temperature stability. You have a noise figure that's very close to the quantum limit of 3 dB for a phase insensitive amplifier that is achieved, and also you have low linearity. And so all these make kind of erbium a very attractive medium of choice. And erbium, of course, beyond being used for line cards and benchtop ADVAs, also forms the basis of narrow line with lasers. And coming back to the topic of optical frequency combs, it's a preferred medium generally to generate femtosecond lasers that make links from the RF to optical, such as those here commercialized by Menlo. And so the question that I've been interested in for some time is, can we make and use and harness these low-loss silicon nitride devices also to make very compact amplifiers? And the ability of the Damascene process with reflow to achieve 1.4 dB per meter provide really the turning point in looking at integrated photonics to provide also a platform for rare earth ions. I should of course mention that there has been many attempts by the scientific community that I unfortunately don't have time to all review, but there's been many efforts already by many groups in the world to try to harness all these beneficial properties of erbium for integrated photonics. But generally the challenge has been, if you categorize all the applications in terms of the output power achieved, okay, from different on-chip solutions versus the on-chip gain, and you compare it to commercial amplifiers, these are sitting, okay, in opposite kind of spaces. Typical commercial amplifiers achieve output powers of more than 100 milliwatt, gains for small signal of exceeding 30 dB. Most solutions in integrated photonics, despite giving large signal gain, reaching values as large as 25 dB, often had output powers that were severely limited in the range of just a few milliwatts. So what are the challenges, okay, to close that gap between integrated photonic based ADVAs and the real commercial ones? And the challenge really is really threefold. The first is because erbium actually has a small cross section and has a limited density of implantation due to cooperative upconversion, it implies you need to actually have very low loss waveguides with low propagation length. And so the low loss is imperative, large interaction length, plus you also need to actually have a large overlap of the ions that give gain and the optical mode. And so despite many groups having tried many different approaches, we've tried one new approach. And the new approach actually that we seeked out was to use ion implantation. And ion implantation has been originally pioneered at Bell Labs by Albert Pullman's group, and is a technique whereby you accelerate, in this case, charged erbium ions and directly implant them into the medium of choice. And this erbium implantation has a number of advantages. One is that its cooperative upconversion factor is lower than other techniques such as co-sputtering. The ion implantation also has the distinct advantage that we can choose by virtue of the energy of the acceleration of how deep to implant the material. And so in this case, what you see here is a simulation in the vertical part actually of our optical mode. We have done, in this case, 3 successful implantation with erbium ions, and thereby achieve actually an overlap factor, okay, that is almost 50% and also confirmed by Rutherford backscattering. Importantly, during this implantation process, actually, there's very little damage to the optical waveguides, and what we see actually in the experiments is that we can keep the original losses within typically 1 dB per meter excess loss. So this shows one of these devices, okay, when being pumped. So this is an example. We have a lifetime, actually in this case, of about 3.4 millisecond, which is to be expected for a high index material such as silicon nitride. We also confirmed the low upconversion factors. And you can see here the extremely compact footprint of this device, which is now, okay, only 3.6 by 1.2 millimeter, okay, with 3 micron gap spacing. And we have here half a meter of spiral waveguide. So, and in the lower part here, you see an optical micrograph actually of the device. So how does this device function and how does it perform? When we pump, we can first look at the on-chip net gain. And here, net gain means here on-chip that we have subtracted the losses actually from the couplers, which are typically 1.5 kind of dB per facet. And what you can see here that in a CNL band, we achieve high small signal gain. For 0.1 milliwatt, we reach 30 dB actually with this amplification method. Now, the real interesting question has been, can we also achieve actually large output powers, which are required for many applications? And in fact, what we've seen, okay, by pumping the device actually bidirectional, we can obtain output powers actually from this chip-based erbium doped waveguide amplifier that reach values of more than 140 milliwatts of power. And so these are significant advances over what has been achieved with other techniques and other materials, and really put, in fact, the erbium doped waveguide amplifiers on par and even exceeding what can be achieved with heterogeneously integrated 3.5s on silicon photonics. And so this establishes kind of a new kind of way to generate very compact erbium doped waveguide amplifiers. And to compare again against state of the art, we can now have both very large small signal gain of 30 dB plus large output powers, and have performance metrics that in fact are very similar to those actually of commercial amplifiers. So let's compare what our performance metrics are. So here's just very briefly only some examples. We can achieve a noise figure of about 7 dB. We can still prove this by getting better input coupling to the chip. We have maximum output power, as mentioned, of 140 milliwatts, so 23 dBm, small signal gain of 30 dB. And I think the technology is interesting from the perspective that it has good performance, but also it's scalable in terms of the manufacturing process, because ion implantation can be applied also to large-scale wafers. Now, what is also interesting is that already today we are kind of achieving a performance metrics that is better than the typical flexoms that are used in telecommunication networks and line cards, and makes this a very first kind of promising technology. Now, I also like to mention that in fact we are commercializing the technology. We are engaging already with first companies in early access prototype studies to test these devices in telecom networks, and so anybody interested actually can contact us, and we have a new company called Luxtelligence actually that's commercializing these devices, so specifically the amplifiers. And these amplifiers can be used for many applications, and I'll give two examples, but examples are amplified light that is needed for LiDAR, amplification that's needed for optical WDM of microchromes, or in general microwave photonics. So to give you one example where these ADVAs can be used. Again, going back to some of the work we did with Christian Kuz on coherent communications, we use silicon nitride optical microchromes for channel generation. So generally, the power in the silicon nitride microchromes is limited. So here we have about minus 20 dBm per chrome line in this early work. And what we've shown actually recently is that using our chip-based erbium doped waveguide amplifiers, we can easily increase that power to 0 dBm. So this shows here in red what comes out of a 100 gigahertz microchrome based on silicon nitride. And we have a silicon nitride ADVA that now takes the chrome lines, actually increases the power, in this case, to close to 0 dBm or above 0 dBm, which is what is needed for telecommunications. Here, an example of a link actually we did over 70 kilometers, showing different constellation diagrams and the bit error rates. And so we demonstrate actually that we can reliably amplify, in this case, more than 20 channels using these erbium doped waveguide amplifiers, and by changing the doping, we could even also access different wavelength bands. Now, so in summary, the silicon nitride low-loss integrated photonic circuits, together with erbium ion implantation, allow us to achieve very high optical gain with large output powers of more than 100 milliwatt, and they have applications in various domains, including microphotonics and communications as described. And we have now prototype commercial offerings using our new company, Luxtelligence. Now, in the last remaining part of the talk, I'd like to switch gear and tell you a bit about another technology that we have spun out from the lab, where we again harness the low-loss silicon nitride, but also endow our silicon nitride platform with MEMS actuators to create a platform that allows to generate frequency agile lasers. And this is the technology that we're pursuing with lab spin-off Deep Light. And so deep light pursues the development of frequency agile laser sources that span the entire electromagnetic range. In principle, they can go as low as 4 nanometers or as large as the mid-IR. And the primary application of these lasers is applications where both narrow line width and frequency agility are required. One example shown on this slide here is FMCW LiDAR. And so what's our ambition? So the ambition is to use the platform silicon nitride we have developed in the lab and address the challenge that exists at the moment in technology. So we have very, very compact lasers that exist in silicon photonics that are used in small pluggables. But in contrast, most lasers, in particular lasers used in the visible for optical, atomic, and molecular physics applications, but also for biophotonics, they're still built using legacy techniques that require you to assemble kind of lasers via optical fibers or bulk elements. And so what we like to do with silicon nitride, and where there's an opportunity, is to close that gap. Silicon nitride is very low loss, it's transparent and visible, and it can be endowed with further functionality that can also achieve very fast laser tuning. And with this, we can address this technological gap and also make more mature, more compact hybrid integrated lasers in different wavelength range that on top are frequency agile. And so how does this function? So technology and really the underlying technology basis has been developed in my lab over the last years, and in which we combined MEMS technology with integrated photonics. And so today, if you have a modern cell phone, what you'll have is so-called F-bar filters. And these are filters that are used to filter the RF signal by converting a microwave signal into a mechanic vibration. So these are transducers from the microwave to the mechanical domain, to phonons. And the way this is done here is to use this aluminum nitride actuators, which are apodized here in this non-hexagonal form. And this is technology that's pervasive. It's used in every cell phone, and it uses aluminum nitride. And ALN has a number of interesting properties. The one is it's a material that has very low hysteresis. It's temperature stable. Plus, it has an actuation bandwidth. That is to say, it has a capacitive response even to very, very high frequencies compared to other materials that are piezoelectric, which typically suffer from leakage currents. And it's a material that's already foundry available and widely used. And together with Sunil Bava, what we've demonstrated in a number of papers is that we can actually combine this material with integrated photonics. And this is an example from one of our papers. I did not put the reference here, but it was a paper on piezoelectric control of solid microchromes published in Nature, where we showed that we can retain the ultra-low loss of silicon nitride, but at the same time endow the devices, with piezoelectric actuation via the stress optical effect. And in contrast to bulk piezos, the actuation bandwidth here can reach in principle frequencies up to gigahertz. In our papers, we demonstrated flat actuation response up to 10 megahertz, up to the frequency of the first H-bar modes. So why is this an interesting kind of combination? You can generate frequency agile lasers. And there's an example where we couple a 3.5 semiconductor diode to a silicon nitride PIC, and by applying our voltage in the self-injection locked regime, we can achieve very fast frequency actuation. Plus, we can narrow the line width of the free-running DFB. So whereas the free-running DFB in an unlocked state has a line width of maybe hundreds of kilohertz or at best or megahertz, it can be locked to a spectrally very pure carrier by using the phenomena of self-injection locking. And so this combination, this hybrid integration, allows us to generate lasers that have this that unify the opposing properties of high coherence and frequency agility. And so to give an example, we can activate the lasers with 10 kilohertz, 30 kilohertz, even 100 kilohertz, up to even to a megahertz of frequency chirp, and generate these triangular signals which are required for FMCW LiDAR, and whose linearity needs to be typically below 0.5%, for doing ranging. At the same time, these lasers have very flat actuation response. This is not actually even this is one of the early devices, not even showing the best. We have flat actuation response today that extends out actually up to 10 megahertz by applying the same techniques and tricks that you apply also in cell phone to apodized filters. So now we have actually completely flat actuation response up to 10 megahertz with these devices. So where do these lasers stand? So these lasers really combine in the metric of line width versus tuning speed what they can achieve is the line width of a fiber laser, but its tuning speed of a semiconductor laser. So we combine these two opposing properties of spectrally pure lasers with fast frequency agility. And typically these two don't go together. Typically the low noise lasers use for fiber sensing are fixed frequency lasers with piezos that are slow to tune, and we can combine these two all in a fully integrated package. And so the application of these lasers are manifold, but in particular in FMCW. So in the last 2 minutes, let me also advertise that as interesting as silicon nitride as material is, one can also ask, can we apply some of our technology also to new materials? And we have been very interested in my group, or I've been very interested in also asking the question, can we achieve similar performance that we have in silicon nitride also in lithium niobate? And lithium niobate has seen over the last years a meteoric rise actually in activity, mostly due to the availability of thin film lithium niobate by NanoLN in China. And so now it's been well established that you can create integrated photonics based on lithium niobate to make very low voltage modulators, electro-optic frequency combs, and many other applications. But if one looks at fundamentally the issue, there's still one issue that has not been solved in the academic community, which is the etching of lithium niobate. To date, the use of rich waveguides shown on the left is pervasive. So waveguides which are only partially etched. And this partial etching, okay, while it may be a desirable feature for modulators, it is mostly due to the fact that traditional hard masks actually erode during the etching process. And that is why it has been very challenging to create tightly confining, thick, say hundreds of nanometers, or in this case 700 nanometer thick waveguides of lithium niobate. And in my lab, we've recently overcome this challenge and demonstrated that using a new hard mask that uses diamond-like carbon, a material that is also used for coatings in razor blades or medical devices, can allow us to create exceptionally kind of steep sidewalls and very thick kind of lithium niobate integrated photonic circuits. And with this, we can make very compact, very tight band radii devices that retain the optical loss properties. And this is an example of such a device. This is our deep edge LNOI technology that we've developed in our lab that's just posted on this archive paper. And already today, we can achieve losses, okay, on the level of less than 8 dB per meter actually in this technology, fully wafer scale. Plus, we retain the sidewall angles that are typical of platforms that are used to make PDKs. So we're very excited actually about this new technology, and also here I like to just advertise. Actually, we are commercializing this technology right now via Deep Light, later intelligence, and it's basically a foundry service for lithium niobate integrated photonics using this new proprietary technology we've developed on deep etching. And so with this, I'd like to thank you for your attention, and yeah, I hope I can still take questions during the break by sharing a Zoom link. And again, thank you very much for your attention.
Tobias, thank you very much for the very interesting presentation. You covered so many new exciting areas. Thank you very much. I'm sure the audience has questions to you, so we have some time for Q&A. There's a question, Thiago, in the back.
Yes, hi, Tobias. Congratulations for such a nice presentation. I have got 2 quick questions, please.
Thank you.
Normally, how much is the output power of the microcomb laser, or someone always needs the amplifier together? And secondly, eventually you might have some optical feedback. Have you ever thought about exploiting some chaos generation with the microcombs, please? Any comments?
Yeah. So I think there are 2 questions. I think I can first actually, maybe I'll start with the second part of your question. I think it was on chaos generation, if you can exploit chaos. And indeed, I should mention, again, I want to give a broad overview of our group, and this, of course, has maybe been at a disadvantage of not covering all the exciting science that exists in these microcombs. But if I just may mention very briefly that solid microcombs, in fact, allow not only to generate stable solitons, which are basically shape-preserving optical waveforms, but in fact also can be chaotic, not necessarily due to feedback, but they're intrinsically chaotic. And so these noisy combs, these MI combs, we have exploited very recently for chaotic random LiDAR. So in fact, we have shown that each of these laser lines in a chaotic state has an innate bandwidth of several gigahertz, so allowing kind of tens of centimeter precision in ranging. And at the same time, in contrast to solitons, they have a very high conversion efficiency. And so here, to generate this chaos, we don't need actually any feedback. The cavity itself generates a chaotic waveform. And the conversion efficiency being close to unity plus noise content that extends over several gigahertz. So I did unfortunately not put the archive reference here, but I'd like to point out that we posted a paper on archive on a random LiDAR based on these modulation stability states in microcombs. This first part of the question was how much power we generate in the soliton carrier frequency comb. So generally there is a fundamental limit of conversion efficiency that exists in these dissipative carrier solitons that has to do with the soliton generation itself, with the bistability. And that means that typically for, say, a 100 gigahertz device, we would have conversion efficiencies that are typically a few percent. And they're very nice, interesting new scientific tricks that have been developed actually by my colleague at Chalmers that allow actually to push that conversion efficiency up by quite a significant factor. But generally, I foresee that for any application that uses these combs for, say, coherent communication, you will need actually an amplifier to reach the power level, say, of 0 dBm.
All right, thank you. Other questions? Yeah, please.
Thank you. Great results. Thanks very much for the talk. My question is about the amplifier part of your talk, and I wonder, what can you tell us about the noise properties of these amplifiers?
Yeah, so on the noise properties, what I can tell you is the following: that we have measured the noise figure of the device. And the noise figure, I think, was in the chart. It was about 7 dB, and it's primarily limited right now by the fact that we have a finite input and output coupling loss, actually, from the facet. That's our dominant addition to the loss to the noise figure. The other part, but that's actually a minor contribution, is still the residual background loss of the waveguides, which after fabrication are 1.7 dB per meter, and then they go up to, say, 3 or 4 dB per meter when we start to add the ion implantation. A very straightforward way to improve actually a noise figure is to improve the input coupling into the silicon nitride photonic integrated circuit, into the PIC.
Thank you. Michael.
Thanks. You talked about 140 milliwatt output power. Is that limit, or can you see it going higher than that?
Yeah, so it's a very interesting question. So can we increase the power of the output? Yes, we can do that. What we have to do in this case is introduce multi-stage pumping. So a lot of the ideas that exist also in the conventional, of course, world of amplifiers, like multi-stage pumping, we can also implement in photonic integrated circuits. And this is exactly precisely what we're actually also aiming to do. Is to pump the waveguide not just with one pump diode, but with several ones at different sections to increase it further. Now, ultimately, how much power could you generate from silicon nitride? And here I want to emphasize or mention one experiment we did about 6 years ago. We have propagated more than 10 watt of optical power through silicon nitride waveguides without seeing actually any Brouillard scattering. So compared to fiber, silicon nitride has a very, very large power damage threshold. So I foresee that one could easily scale up the output power probably to a watt. The limitation in this case becomes just from back reflection of the facets. Because at very high gains, you become very sensitive to back reflection and can get parasitic lasing. So that is, I think, the main challenge, okay, for large gain amplifiers.
For what you just mentioned, what is the waveguide dimension for the 10 watt?
Oh, this was the waveguide dimension for 10 watt that we showed. It was early work on microcomb generation. There we had 2 micron waveguide, a width and a height of 800 nanometer.
So very high power density.
Very, very high. Intensities are exceptionally high, and we see no Brouillard scattering as opposed to optical fibers where you would have the back reflection. from
Thank you.
SBS.
Yeah, Frank.
Excuse me. Really nice talk, Tobias. Thank you. I'm just wondering quite a general question about, let's say, time to market for some of these hybrid and heterogeneously integrated integrated circuits.
Yeah.
Thanks.
So maybe I'll start with briefly with Deep Light. So with Deep Light right now, we have started a company with my colleagues Christian Koos and Neil Bave. It's a bit more than a year old, and we are today shipping early access demonstrators. So if anybody in the room who is interested, I'm happy to put you in contact with our company. You can email me directly to my EPFL address. We believe right now that these lasers actually have merits and have a market because they combine these opposing properties of narrow line with end frequency agility. In terms of technological readiness level, I think as far as least as the PICs are concerned, this is a very mature technology. So the manufacturing of the circuits is foundry, both from the perspective of the optical waveguide technology as well as from the MEMS. I think this technology is one which is really, which we have commercialized. So if you're interested, as I said, I can put you in contact with for the lasers with our team of Deep Light. When it comes to the amplifiers, this is a recent development, but we are engaging actually in prototype commercial offerings. So we have received, I cannot say names, but there's a lot of interest in this technology for telecom, evidently, but also other applications. And we are shipping packaged devices with integrated pump lasers and fiber coupled devices for testing, and where we can meet the requirement of the specific applications in terms of the power, in terms of the noise figure, in terms of the small signal gain. And I think the TRL level of this technology is absolutely identical to the lasers. In fact, it's even a bit lower because of the simplicity of the functioning principle of an amplifier compared to a laser. So I hope this answers the questions. And again, I can't resist also to share. Again, I apologize, but I have to just mention my excitement about lithium niobate and insulator, because what I've been very surprised by, it took us in my research group about 5 years of work to really optimize the propagation losses of silicon nitride. And with this new etching based on DLC, diamide-like carbon, these protective coatings, we can get losses right now of lithium niobate already that are below 8 dB per meter while retaining the form factors. And I expect that this foundry offering could fuel a new generation of modulators, of filters, also of lasers. And we like to, similar to Ligentech, we like to provide this now to the community and also to startups, to academic customers, to big companies as a foundry offering.
Thank you. Michael is showing his hooves.
Can you say a bit about how you couple the pump laser to the circuit?
Yeah. So in general, the way this is done, I'll just use a slide of lithium niobate here, but it's done the same actually also for silicon nitride, is we make something called double inverse tapers. And this is a technology that was originally developed by my colleague Michael Lipson at Cornell. It's simply taking a waveguide and tapering down its width. In the case of silicon nitride, we can do something a bit more elaborate. We can not only taper the width of the waveguide, but also the height. And that's a specific property of the Damascene process. So we have a conical taper where we can increase the mode size substantially to directly interface with an SMF28 fiber. And so the best coupling right now that we have achieved in our lab is a 3 dB. No, sorry, it's 80%. Sorry, it's 3 dB, so 50% transmission, fiber to fiber with the chip in the middle. So it's 25% loss per facet. There are ways to increase it even further, but of course, those require a bit more complexity. This is just a single layer solution.
Right, but that's to fiber, but how about the actual 3.5 laser chip?
That's just hybrid integration. So for instance, in the case of our technology that we are commercializing with Deep Light, so the lasers, what we have done here is a very simple kind of hybrid integration technique where we have waveguides that match actually the mode diameter of the 3.5. Yes, exactly. Yeah, yeah. And there's another very interesting technology we're pursuing, which is photonic wire bonding with Professor Kirsching-Koos, which can serve as a very interesting technique in terms of scalability and manufacturability. For the moment, our prototypes right now for the technology demonstrators of deep light and also for the amplifiers are based on hybrid integration. And the best 3.5 to silicon nitride coupling that we have seen is actually 50%. So it's compounded by our imprecise knowledge of the optical mode of the 3.5.
Okay, the quick
Yes,
question with a quick answer.
Yeah. You mentioned 80% coupling directly with SMF fiber to SMF fiber. Is this offered as a standard PDK in Legentech, this direct coupling to SMF?
Yeah, Legent, absolutely. So Legentech has a proprietary technology that I'm not allowed to share like how it works, but Legentech has in the AN800 process, so 800 nanometer thick nitride core, they have directly SMF28 to SMF28 with 3 dB loss. That's it. They offer commercially. They offer this, and they do this using spot size converters. So that's yeah, it's commercial offering. Yes.
Okay.
Thank you. Fortunately, we're running already out of time. Do we have any quick question on the chat? Oh, great. I was worried you said yes. Okay.
So I think thank you very much for the talk and also many questions. And I reiterate, I'll be very happy to chat via Zoom with anybody today, or you can send me an email to my EPFL address, tobias.kippenberg@epfl.ch, and you will have definitely my attention and my answers.
Yeah, thank you very much again.
Thank you.
Unfortunately, as always, time flies, and now we need a short 2-minute break to move also to the other room. Peter, if you could please show the schedule from the intro presentation, because I would just like to remind everybody which session you might want to join. So in this room, we stay in session A.